In November of 2022, NASA left the SLS rocket on the pad while a hurricane was approaching. Now, why on earth would they do that, considering the risk?
That's a beautiful rocket you have there. It'd be a shame if something happened to it.
So why would you actually run that risk? They had already, in fact, moved the Artemis out of the path of Hurricane Ian, even though that wasn't as much of a risk. It turns out that there's a budget for how many moves you can do. And that budget is not a financial budget, it's an engineering budget. It basically means that every time this vehicle gets moved, there's going to be lots of vibrations and shaking, even with that crawler transporter going so slow. And those vibrations and shaking are going to cause something called work hardening, which creates cracks. This is an example of what the kind of work hardening cracks you'd expect to see, which you could well imagine is not the kind of thing you want to see on a rocket. And here I'm doing a simulation of the crystal lattice and what happens when you apply stresses to it. And this is in no way just some steel balls on a magnetic sheet, but oh hey, at least there's a nice graphic overlay. And this overlay is there simply to highlight where the crystalline order is and where there's disorder. And so it's a good way of visualizing where there are grain boundaries on this. And so what you can see is that as this gets compressed and pushed and stressed, it's going to start producing smaller and smaller domains. And the smaller domains lead to more brittle fracture rather than the plastic deformation that you can get with the larger domain sizes and the atoms slipping past each other. So this corner of the aluminum here, since it was drawn and then bent, means that this should be much more work hardened than, say, this part right here. And now, one way that we can undo the work hardening when it comes to aluminum is to heat it up. So I'm going to try that on one side, and we'll leave the other side alone, and we'll see what the difference is when we go to break it. Okay, so this is the side that I did not do the heat treating on. I just put a mark there so I could see that. And I'm going to give this a bend, and we'll see how this goes. Okay, that folded in. And now, like one, and you can see the crack forming there. There we go. That broke off, and it is classic work hardening. Now, let's see what happens on the other side. So this is the side that I heat treated, and let's see what happens. Definitely easier to fold. So I'm starting to see maybe a sign of a crack there, and it certainly is causing a lot of stress in that spot. Now it's opening up. And that did crack there. And still, yeah, I have to like really tear this to get that. Yeah. And yeah, so that was not really work hardened there. You can see the way it bent like that. It's not the same as the other side that you can see as much sharper break on it than that. And probably not so easy to see. And this one, more smoother. I mean, it's still kind of serrated, but not as bad. And here you can also just see that it underwent more of a plastic deformation, where this one you can very clearly see snapped. And that is the difference between the work hardening and not.